Welcome to this presentation on trapping rainwater the second. Today we will explore the problem statement, approach, code implementation and complexity analysis to understand how to efficiently solve this problem. Let's start with an introduction. In this problem, we are given a 2D elevation map represented as a grid of integers. Each cell represents the height of the cell in the map. The goal is to calculate how much rainwater can be trapped between the cells after it rains. We will go through the problem statement and its constraints, then learn an efficient approach using a priority queue, and finally analyze the complexity of our solution. Here's the problem in detail. We need to calculate the total amount of rainwater trapped after a rainfall on a 2D elevation map. The water can only be trapped between higher boundaries and the water cannot accumulate on the grid edges. The challenge is to find an efficient way to compute the amount of water trapped while respecting the given constraints on grid dimensions and boundary conditions. The key idea behind our solution is to use a priority queue or main heap to process cells in increasing order of their heights. We begin by processing the boundary cells which form the limits for where water can be trapped. By comparing the heights of neighboring cells, we can calculate how much water can be trapped at each cell. This approach ensures we process the lowest boundary first and avoid unnecessary computations. Let's visualize the algorithm with an example. Here is a 2D grid. Initially we add all the boundary cells to the priority queue. The cells inside the grid will be processed based on their height, starting with the smallest boundary. As we process each cell, we check its neighbors and calculate the amount of trapped water based on their relative heights. Let's take a look at the code. First, we define our solution class and the trap rainwater function. We handle each edge cases where the grid dimensions are too small to trap any water. We initialize a priority queue and a visited array to track the cells we have already processed. Then we add all boundary cells to the heap. Now let's focus on the initialization part. We loop through the grid and add all boundary cells to the priority queue, marking them as visited. Boundary cells are crucial because water cannot be trapped there and they act as the initial boundaries for the algorithm. Next, we move to the main part of the algorithm. The goal is to process cells in increasing order of their heights. We extract the cell with the smallest height from the heap and check its neighbors. If a neighbor is lower than the current height, we calculate the trapped water and add that neighbor to the heap with its updated height. This slide handles the logic for processing each neighbor. For every unvisited neighbor, if its height is smaller than the current height, we calculate how much water can be trapped there. The trapped water is added to the total count and we update the neighbor's height, pushing it back into the priority queue. Now let's look at the complexity of the solution. The time complexity is big O of m times n log m times n, where m and n are the dimensions of the grid. This comes from processing each cell once and performing heap operations, which are logarithmic in nature. The space complexity is big O of m times n, since we need to store the visited array and the priority queue, both of which can hold up to m times n elements. Let's walk through an example. Here is the input grid. We begin by adding the boundary cells to the priority queue. These cells form the boundaries that determine whether water can accumulate. Next, we process the smallest height cell in the heap and calculate the trapped water for its neighbors. Continuing with our example, we repeat the process of extracting cells from the heap and calculating the trapped water. The trapped water accumulates in the valleys formed by higher cells. After processing all the cells, the total water trapped is 4. This is the final output of this grid. To summarize, we solved the trapping rainwater, the second problem, using a priority queue to process boundary cells and their neighbors in increasing order of height. This approach ensures an efficient solution with a time complexity of big O of m times n log m times n, which makes it suitable for large grids. We also discussed real-world applications such as simulating water flow and predicting floods. The key takeaways is the importance of understanding the 3D water trapping logic and optimizing the solution using a main heap. Thank you for your attention. We have covered the problem, the approach, code implementation, and the complexity analysis. If you have any questions or need further clarification, feel free to ask now.